Welcome. In this video, we are looking at the fundamentals of Python, the first program, second edition. This is for the book ISBN 1097813375600092. All of this material is copyrighted by Cengage. They own the rights and the book. The assumption is that you have the textbook. I'm going to be providing just video lectures on the content in the official PowerPoints. My name is Arthur Salmon, and I'm going to be working with you throughout this course. Chapter 1 is a basic introduction to programming. The main objectives is to describe the basic features of an algorithm, explain how hardware and software collaborate in a computer architecture, give a brief history of computing, and lastly, compose and run a simple Python program. So let's jump right in. Computer science focuses on a broad set of interrelated ideas, typically dealing with technology support, and other information-centric concepts. Two of the most basic ones are algorithms and informational processing. So, for example, let's look at algorithms. Steps for subtracting two numbers. We have a 4-step process. Step 1, write down the numbers, the larger above the smaller one. Realistically, if we are doing subtraction, we would list them based off of order, not rank them greatest to least. So there's some differences because, again, order matters. But the assumption is order in this doesn't really matter in this example, so write down the numbers, larger to smallest. Start with the rightmost column of the digits and work your way left through the various columns. Write down the differences between the digits of the current column of digits, borrowing a 1 from the top number if necessary. Step 4, if there is no next column to the left, stop. Otherwise, move to the column to the left and go to step 3 and repeat. So the computer agent, the person using the device, acting on behalf of the user, is typically a person. It's a human. So a sequence of steps that describe each of these computational processes is called the algorithm, is the actual process. So features of an algorithm consist of a finite number of instructions, the steps. Each individual instruction is very well defined. The structure is organized and agreed upon. Actions described by the instructions can be performed effectively or be executed by a computer agent. That will be the actual computational device. We will be describing the process that eventually halts after arrival at the solution. After the execution of the program or steps, a final solution should be able to be there. If we're looking at two numbers and we're subtracting the two, once each of the columns has been subtracted, that would be the natural conclusion of that program. So computers can be designed to run a small set of algorithms for performing specialized tasks, and so forth. Some of the tasks are called informational processing. So essentially, information is also referred to as data. Normally, data is raw, and information is some type of structured data that has meaning. So to carry out the instructions of an algorithm, a computing agent will manipulate information. It starts with input, that will be data. There will be some type of transformation in accordance with our rules, some type of execution of a feature or a function. This will produce an output. The algorithms that describe information processing is also represented as information. Computer scientists recently discovered how to represent many other things, such as images, human speech, video, music, and so much more in our digital formats. So a modern day system consists of hardware, that's physical, and software, that's typically intangible, things that we cannot specifically touch. So when we are dealing with software, it's dealing with the programs This could also be a set of algorithms, and the programs themselves, the algorithms themselves, are written in a language typically referred to as the programming languages. A program could be written in multiple languages, or it can be written in a common language. It just kind of depends on the type of program. The computer hardware typically will have things like its memory, its processor, and its I/O, input-output devices, keyboard, mouse, monitor, for example. It could also be as simple as reading a file input, computational or execution, and then output could be a printer or a display, things like that. So computers can also communicate with the external world through various ports and through other means like a network. So just because we are doing a local resource doesn't mean we can't share it with the rest of the world, because we can. Computer memory is set up to represent stored information in electronic forms, binary. There are two types of memory: long-term storage, that's hard drive, or temporary storage, that's going to be more like workspace, that's called random access memory, or RAM. And RAM is the primary internal memory. We have other parts of the computer like the processor. This is going to be what is used to process and compute the algorithms and other forms of data. And again, external or secondary memory is going to be that long-term storage, like hard drive. Here we have a row of cells, and we have a column of ones and zeros. This essentially is what computer memory looks like. We can convert everything to a digital format represented by ones and zeros. And this is how memory actually looks. So for a program stored in memory, it must be represented in a binary, or also known as machine code. While there are versions of binary being ones and zeros, we could have hexadecimal, which is also 1 through 9 and A through F. Those also work. All of these allow us to convert it back down to binary. A loader will take a set of machine language instructions, and it will take them as input. It will load them into the appropriate memory location. The most important example of the system software, for example, is the operating system. The loader will load the operating system into memory and allow a user to interact. There are different parts of this operating system, things like the file system, user interaction, terminal versus a graphical touch screen, and so forth. And then there's the additional content on top of the operating system. That's going to be applications, Word, PowerPoint, Excel, a web browser, games, and so forth. Scientists have developed a high-level programming language for expressing algorithms. While it may resemble English, and it also allows the author to express algorithms in a form that other people can understand. Programmers usually start by writing high-level programs in a text editor. The text editor will run other programs, and basically it's called translate, to convert a program code into some type of executable code. And if there is a translation error or a translation issue, typically this is known as a syntax error. If you're not following the rules, then the translator doesn't know how to translate the code that you are writing. So you might execute a program directly on the hardware, or run another program called an interpreter or a virtual machine to execute the program. The interpreter is just another way of saying a program that will read and execute the code. Here's an example of a text editor going into a translator. If there's a syntax error, then we're going to get an error message. If no syntax error exists, the translator will send it down to a runtime system. The runtime system may also take user input. Again, if there is a syntax error, it may kick it out as an error. If not, then we'll get an output, or program-based output. And this is a pretty common review of how applications function. So now that this provides a basic understanding of what software is, let's take a look at a brief history. Again, before 1800s, mathematicians discovered and the use of algorithms. We had things like an abacus. We had the 19th century, which again we use Boolean system logic. In the 30s, we started turning publishes for computational abilities. In the 30s, we also had the forming of digital-based switching. In the 40s, we had electronic digital computers. 50s, we started having our basic programming languages, and it just grew from there. From early 2000s, we've now had pretty much anything represented in a digital format. Digital streaming like music, videos, and other content are now commonplace. Nope, I went too far. So again, an algorithm comes from Muhammad, I can't pronounce his name. He's a mathematician. He developed an algorithm for computing the greatest common divisor of two numbers. We also had an abacus. I'm going to show you an abacus on the next slide. Again, these are all famous people that aided in the construction of mathematicians and our algorithm understanding. Here's an abacus. Here's a different type of calculator. And again, all more recent individuals. Alan Turing, for example, born in 1912, died in the 50s. He explored the theoretical foundation and limits of algorithms and computation. In the 30s and 40s, we had groups, now businesses, that were being built to build digital-based systems. You'll notice in the 40s we had a mainframe computer, and it consisted of vacuum tubes, wires, and plugs, and it filled an entire room. It was large. In the 50s, we had our first assembly language. It had operators like add and output. Programmers entered code for the operations in a key punch machine. There was a reader that would translate the holes into patterns into the computer memory. Then there was an assembler that would translate the application program in memory to machine code. And then there was the compiler that would translate the machine code into a program. This was a high-level programming language, like things like Fortran or COBOL. In the 50s, vacuum tubes went away, and we started getting transistors. Transistors is basically a solid-state device. Early 60s, we had integrated circuits. We had microcomputers starting to appear, and we had processing evolved from what was then batch processing to time sharing to concurrent processing. Late 60s, again, we had the first appointed device, the actual mouse. In 75, Altor started doing the mass-produced personal computers using the Intel 8080 processor. This was the first true microcomputer chip. Early 80s, we had Gates and Allen build MS-DOS. We had Bob build and use Ethernet used in networking. We had ARPANET, that became the internet. Now we have things like optical storage, CDs, DVDs, Blu-rays. We have virtual reality. We have other forms, things like internet features, HTTP, hypermedia, streaming media. All of this were major growth components of the World Wide Web. That means online content. The nice thing is, part of the World Wide Web are things like web servers, web browsers, and clients. That's going to be us. Furthermore, web applications have taken off as well. Made online stores, for example, microtransactions, playing games. You can now buy, outfits for your favorite character in small online games. You can now do online games. So all of this kind of started building to additional technology to aid the individual. We had things like PDAs, personal digital assistants. Those kind of went away but we had things like that were eventually replaced with things like iPhones and iPads and iPods. These types of devices allowed us to have a better understanding of video games, address books, to-do lists, note-taking, personal assistants, calendars, all in one device. This also aided in the social networking, being social. This also allowed us to start collecting mass amounts of data on individuals, better figure out how to market. Well, marketing is just one aspect of big data, but to figure out better programs as well. Early 90s, we had Python being invented. Again, Python is a high-level, general-purpose programming language for solving problems on modern-day computer systems. Python is an interpreted language. Essentially, Python will express and it will create statements that can be ran in a shell. Easiest way to open up a Python shell is to launch the idle. Again, idle is going to be one of the programs we have working to do our Python in. It will create our shell. Our shell is basically going to be experimenting with short expressions or statements at the end of our PowerPoint. This is what our shell will look like. After the 3 carets, we can actually start typing in commands. For example, we can do a print and an expression, and we should be able to get our output. We will tell the device with an input message, input with the appropriate syntax, and then we will be able to run it, and it should be displayed. Issue here is this will only display what we type. Here we have an example, receive an input from a string from the user, and we will save it so that we can process it a little bit later. From here, we can then use it to recall some information. Alright, so let's go ahead, and I have a Windows machine with our Python installed. I'm going to go ahead and try doing this example. I'm going to do a variable name that equals an input from our user. So we'll do a parentheses, double colon, or double quotes. What is your name? Question mark. I'm going to do a space and then another end quote in parentheses. I'm going to hit enter, and it will prompt me. If I didn't do the space, then the cursor would be right next to the question mark, and I don't want that. I'm going to type in my name. So now we stored our variable name. We stored my name in that variable named name. So now we want to go ahead and print it out. So we'll do print name in parentheses, hit enter, and it now prints out my name. Again, very simple program. So from there, the input function will always build strings from the user's keystrokes, and it typically returns it to the program. Strings that represent numbers must be converted from a string to the appropriate number type. For example, there are 2 main conversions, integer, int, or a float. The float will be for a floating point number. An integer is typically a whole number. For example, the next session input, we could do 2 integers. Enter the first number, enter the second number, and we can then add the 2 to create the sum. Alright, so I'm going to go ahead and type that in. I'm going to do first equals input. First is going to be int, because we want to make sure that we're changing this to an integer, so it'll be input, parentheses, quotes, what is the first number? I'm going to do space in quote, in parentheses, Again, the first set of parentheses match up there. The second one matches up there. I'm going to run it. I'm going to add, first number is going to be 10. The second number is second. Again, I want to keep it as an integer. Input. What is the second number? Space, double quote. One parenthesis ends beginning of the text. Second parenthesis ends the integer portion. I'm going to add the number 5. And I'm going to do one more option. I'm going to do a print. I want to sum the number. So I'm going to do quotes, the sum of the two numbers is space, in quote, I'm going to do a comma, first plus second. I only need one parenthesis because I'm going to be closing it at the very beginning. Hit enter, and it will print out my statement and do the computation. If I want to see the product, the product of the two numbers, and you can manipulate it from there. Again, this int basically says whatever the character is entered, make sure we save it as an integer. So I want to do a third number, so I'm going to do third equals int input parentheses double quotes, what is the third number? Space, double quotes, in parentheses, hit enter. Oh, it did not like that at all. I misspelled input. Input. And it will ask me for the third number. What happens if I do a character? An integer, because we declared it as a int, means it'll only accept whole numbers. If we try doing this again, and we do 1.5, 1.5 is not a whole number. So we have to keep that in mind. Whatever our character types are, they do matter. So our character types are things like float or integers. If we want to do an input, we will basically be capturing an input. If we want to print, we could print the output. And we can do multiple expressions by doing one expression, comma, another expression. If we want to add two strings together, it would be string plus string, and so forth. The strings would be uniquely identifiable, of course. It wouldn't just be the word string. We would declare a variable and so forth. That is going to be a little bit covered later as we start talking about our variables and our variable types. We can run the Python program file as a whole. That's going to be called a script. Most scripts have either an idle or the ability to run a script through our command line. So when we're running our idle program through Windows, we can look at options with F5. Our program, anything dealing with our Python scripts are going to be labeled with a .py extension. That is how the program, Windows, knows that our Python scripts are belonging to Python. So running a script from the idle allows you to construct some more complex based programs and allow us to test them. Essentially, we're going to be saving them through program libraries. That way we can reuse the program a little bit later. if necessary. Here's an example of what we would have been doing. We could ask for input, height and width. We could do our calculation, and then we could do a program call. Well, we could save this as a script, and then we can keep calling it as much as we wanted to. That way, we could save it, and we can run it whenever we needed to. So behind the scenes, again, we have our Python code checking if there's no errors. It will be sent to the translator. It will be sent through our bytecode to our Python virtual machine. Our Python virtual machine will take user input, verify, and it will provide our output if necessary. If there's an error message, it will display the error message instead. So programmers might make errors. It is what it is. Those are typically called syntax errors or bugs. The Python interpreter will usually detect them and alert you. There are rules, there are syntax for forming sentences in any language. Syntax is just a clever way of saying rules or structure. So when Python encounters a syntax error in a program, for example, it halts. When I fat-fingered input instead of input, it was intput. That actually would then translate to a error, and it would alert us in red, and that's what it did. And then it actually would define what was going on in most cases. So our example could be as simple as 3+ and hit enter. The system doesn't know how to do that because it's expecting 3+ something else. So it's not expecting a operator, the end by itself. So that was all we had for our first intro lesson. We're going to be talking about variable types a little bit later. We're going to be getting more in depth a little bit later. But this is just an introduction to computer science, input-output process, and so forth. So make sure you understand algorithms, information processing, the hardware portion of the computer, what a program language is, understand what Python is, understand that it's a higher level language. An interpreter that translates a Python program to a lower level can also be executed on a real computer. Those are going to be lower level programs. Python shell provides the command prompt, the processing ability to view and execute our code. We're going to be using idle as an integrated development environment that allows us to be able to program and save our code. Python scripts are going to be saved in a file with a .py extension so that we can operate and run them later. Lastly, when a Python program is executed, it is executed into bytecode, sent to the Python virtual machine for interpretation and execution, and as long as there are no syntax errors, it should display the output. And again, syntax is a set of rules for describing our code. Thank you. So as we finish up, if there are any questions or concerns, please feel free to reach out. Again, some of this content may be new to you, so instead of struggling, ask questions. Remember, as you ask questions, it also helps with data retention and information retention, so engage. If I can do anything to help, let me know. Thank you.